Chapter 3 Matrices, Class Number 2. The sum of two matrices is a matrix obtained by adding the corresponding elements of the given matrices. Furthermore, the two matrices have to be of the same order. If capital A and capital B are standard 2 by 3 matrices with individual elements of the form Aij and Bij, where I goes from 1 to 2 and J goes from 1 to 3, then the sum of these two matrices is another 2 by 3 matrix whose individual elements will be of the form Aij plus Bij. An example of the same is given in the slide. Multiplication of matrices. We can define multiplication of a matrix by a scalar as follows. If capital A is a matrix of order m by n, and small a ij is any representative element of the matrix capital A, then Ka is another matrix, which is obtained by multiplying each element of A by the scalar k. Example of matrix multiplication is provided in the slide. Negative of a matrix is defined as minus A. We define minus A is equal to minus 1 multiplied by A. Concept: difference of matrices. If capital A and capital B are matrices of the same order, say m by n, then difference of A minus B is defined as a matrix D, where each element of D represented by small dij is equal to small aij minus small bij, where small d, small a, small b represents an element of the corresponding matrices. Alternatively, we can represent D as sum of the matrix A and the matrix minus B. A solved example of matrix subtraction together with matrix multiplication is shown in the slide. Concept: properties of matrix addition. Commutative law. If A and B are matrices of the same order, say m by n, then A plus B equals B plus A. Associative law. For any three matrices A, B, C of the same order, say m by n, bracket open A plus B bracket close, plus C equals to A plus, bracket open B plus C bracket close. Additive identity. Let A be an m by n matrix and O be an m by n0 matrix. Then if A plus O equals O plus A equals A, then O is the additive identity for matrix addition. Existence of additive inverse. Let capital A equal small aij be any matrix. Then we have another matrix as minus capital A, where general element of minus A will be minus small aij, such that A plus minus A is equal to 0. Then minus A is the additive inverse of A. Sum number 1. A is a 3 by 2 matrix with elements 8, 0, 4, minus 2, 3, and 6. B is another 3 by 2 matrix with elements 2, minus 2, 4, 2, minus 5, and 1. Then find the matrix X such that 2A plus 3X equals 5B. We have 2A plus 3X equals 5B, or X equals 1/3 of 5B minus A, where A, B, and X are matrices. Now, replacing the value of matrices B and A in this equation, we get the elements of the matrix X. Find the values of x and y from the given equation. Multiplying the left-hand side matrix by 2, we get the following. Equating the elements of the two matrices of LHS and RHS, we can compute the value of x and y. Concept: product of a matrix. Let capital A be an M by N matrix, capital B be an N by P matrix. Let small aij represent a sample element of matrix A. Let small bjk be a sample element of matrix P. Then the product of the matrices A and B is a matrix C of order M by P. Consider a matrix A with m rows and n columns. This is depicted in the slide. The ith row of matrix A is highlighted in black. Consider a matrix P with n rows and p columns. This is depicted in the slide. The kth column of matrix P is highlighted in black. Once we multiply matrix A by matrix P, it will result into a new matrix C. The representative element of matrix C, which is given as an element which is in row number I and column number k, will have the following value. In the next slide, we will provide examples to make this computation clear. Examples of matrix multiplication. Let C be 2 by 3 matrix. Let D be 3 by 2 matrix. Both will have 6 elements. The product of C and D will result in a new matrix CD, which will be of order 2 by 2. The elements of new matrix CD will be computed from the elements of the original matrices C and D as shown in the slide. Sum number 3. Find the product of the matrices A and B. A is a 2 by 2 matrix. B is a 2 by 3 matrix. The elements of the matrices are given in the problem statement. The matrix A has 2 rows and 2 columns. The matrix B has 2 rows and 3 columns. The resulting product matrix will be a 2 by 3 matrix. The elements of the new matrix will be computed as shown in the slide. This is obtained by multiplying each row of matrix A by each column of matrix B. If AB is defined, it is not necessarily true that BA will also be defined. In this example, while AB is defined, BA is not defined. The reason being B is a 2 by 3 matrix and A is a 2 by 2 matrix. And since the number of columns in B does not match the number of rows in A, BA is not defined. If both A and B are square matrices, then AB and BA both are defined. Sum number 4. A is a 2 by 3 matrix. B is a 3 by 2 matrix. The elements of A and B are displayed in the problem statement. Find AB, find BA, and show that AB is not equal to BA. According to the rules of matrix multiplication, dimension of AB will be 2 by 2, dimension of BA will be 3 by 3. In the above example, both A, B, and BA are of different order and hence are not equal. However, it is not necessary that if A, B, and BA are of the same order, they will always be equal. Concept: Properties of multiplication of matrix. Associative law is applicable for matrix multiplication concerning three matrices A, B, and C. Similarly, the distributive law is also applicable for multiplication of matrices. Existence of multiplicative identity. For every square matrix A, there exists an identity matrix of same order such that IA equals AI equals A. Sum number 5. Three matrices A, B, C along with their elements are given in the problem statement. A is of the order 3 by 3, B is of the order 3 by 2, and C is of the order 2 by 4. The requirement given in the problem statement is find a multiplied by bracket open B into C bracket close and bracket open A into B bracket close multiplied by C. Show that these two matrices are equal. Multiplying the product of matrix A and B with C, we get a 3 by 4 matrix whose elements are computed in the slide. Sum number 5. Three matrices A, B, C along with their elements are given in the problem statement. A is of the order 3 by 3, B is of the order 3 by 2, and C is of the order 2 by 4. The requirement given in the problem statement is find a multiplied by bracket open B into C bracket close and bracket open A into B bracket close multiplied by C. Show that these two matrices are equal. Multiplying the matrices B and C and computing the elements we get. Finally, multiplying the product of matrices B and C with matrix A, we get the below result. Clearly, the two computed matrices are equal and hence the relation mentioned in the problem statement is correct. Sum number 6. Given A is a square matrix of order 3 by 3, whose elements are mentioned in the problem statement, show that A cube minus 23, A minus 40, I is equal to 0. First, we compute A square. By multiplying matrix A with itself, we get another 3 by 3 matrix with values as shown. Next, we compute A cube by multiplying matrix A square with A, and finally bring identity matrix as the third element of the LHS in problem statement. Computing the values of A cube minus 23, A minus 40I, we see that the LHS in problem statement is a zero matrix. Sum number 7. F of x is a 3 by 3 matrix with elements given in the problem statement. Prove that f of x multiplied by f of y is equal to f of x plus y. F of x is a 3 by 3 matrix with elements cosine x minus sine x 0, sine x cosine x and 0, 0, 0 and 1. Similarly, f of y is a 3 by 3 matrix with elements cosine y minus sine y 0, sine y cosine y and 0, 0, 0 and 1. As per the problem statement, we multiply these two 3 by 3 matrix to compute the value of f of x into f of y. Performing row by column multiplication the matrices. Sum number 7. F of x is a 3 by 3 matrix with elements given in the problem statement. Prove that f of x multiplied by f of y is equal to f of x plus y. We see from the computation provided in the previous slide that once we multiply the matrices f of x and f of y, we get a new 3 by 3 matrix. The elements of this 3 by 3 matrix will be equal to the elements of f of x plus y. Hence, LHS is equal to RHS. Sum number 8. Given a 3 by 3 matrix, compute the value of a square minus 5a plus 6 of I. Performing matrix multiplication, we see that the matrix A square is a 3 by 3 matrix and its elements are 5 minus 1 2, 9 minus 2 5, 0 minus 1 and minus 2. Before computing the final step, we need to convert the I given in LHS into I3. The reason being we are dealing with all 3 by 3 matrices and hence identity matrix in the computation of LHS should be 3 by 3. And we know that identity matrix of any order has the same value and can be interchanged as per our calculation requirement. The final value of the LHS is a 3 by 3 matrix whose elements are 1 minus 1 minus 3, minus 1 minus 1 minus 10, minus 5, 4 and 4. Sum number 9. If A is a 3 by 3 matrix with values given in the problem statement, prove that A cube minus 6A square plus 7A plus 2I is equal to 0. First, we compute A square. Next, we compute A cube by multiplying matrix A square with A. Before computing the LHS in our problem statement, we will first convert the I, that is identity matrix, given LHS, into a 3 by 3 matrix to ensure compatibility with the order of other matrices. Sum number 9. If A is a 3 by 3 matrix with values given in the problem statement, prove that A cube minus 6A square plus 7A plus 2I is equal to 0. Continuing the same problem from the previous slide, we now compute the LHS of the problem statement. Hence, we see LHS is a zero matrix, proved as required in the problem statement. Sum number 10. If A is a 2 by 2 matrix with element 0 minus tangent alpha by 2, tangent alpha by 2, 0, and I is the identity matrix of order 2, prove the relationship given in the problem statement. We can write I as a 2 by 2 matrix with elements 1, 0, 0, 1. Next, we compute LHS by adding the identity matrix to A. The matrix I minus A will be sum number 10. If A is a 2 by 2 matrix with element 0 minus tangent alpha by 2, tangent alpha by 2, 0, and I is the identity matrix of order 2, prove the relationship given in the problem statement. Next, we perform matrix multiplication of the 2 by 2 matrix given in the RHS. We continue solving the sum number 10, moving ahead from the step arrived at the previous slide where RHS is simplified by doing a matrix multiplication. In the previous slide, we saw the RHS is simplified to the 2 by 2 matrix depicted here. Upon simplification, we can see that each of the elements of the matrix takes the form of trigonometric equation in A and B. The elements of the matrix is equal to 1 minus tangent alpha by 2, tangent alpha by 2, and 1, which is equal to the LHS value, as computed in slide number 20. A trust fund has 30,000 rupees that must be invested in two different types of bonds. The first bond pays 5% per year. The second bond pays 7% per year. Using matrix multiplication, determine how to divide rupees 30,000 in two types of bonds so that the interest obtained is A 1,800, B 2,000. We can solve the given problem using matrices by creating two matrices, a 1 by 2 matrix dividing the total amount of 30,000 into two parts, and a 2 by 1 matrix depicting the interest rates. For I equals 1,800, solving the above equation, we get x equals 15,000. In this case, we need to divide the total into two parts of 15,000 each to arrive at interest rate of 1,800. Similarly, for I equals 2000 and solving for x, we arrive at the answer. That is, we need to divide the fund into 5,000 and 25,000 to receive a total interest of 2000. Sum number 13. Matrix P is of the order P by K. Matrix Y is of the order 3 by K. Matrix W is of the order n by 3. The restriction on NKP so that PY plus WY is defined will be choose from the given options. Since matrix P is a P by K matrix and Y is a 3 by K matrix, for Py to be defined, K has to be equal to 3. The matrix Wy can be defined, irrespective of the value of n and k. For adding matrices Py and Wy, these matrices need to be necessarily be of the same order. Wy is of the order n by k as depicted in the previous step. Py is of the order p by k. This is obtained by deducing that k is 3, which makes the order for py to be p by k from the first step. Hence, p is equal to n. Hence, option A is correct. End of class 2 on matrices.